In this video here, we're going to take a look at oblique impact with a fixed surface. Now we can solve problems involving the oblique impact of a smooth sphere with a smooth fixed surface. Now an oblique impact is one where the particle does not strike a surface normally. And we usually use alpha and beta to represent the angles between the path of the particle and the surface before and after the impact. And this diagram below here should hopefully help illustrate this concept, right? So I've got this dot here. This is just our particle here, our smooth sphere. So it moves towards the fixed surface here. So this line at the bottom, this is my fixed surface, okay? So I'll draw the lines here underneath just to represent that this here is our fixed surface, right? So the particle moves towards the fixed surface and it strikes the fixed surface here in a way that is not normal, okay? In other words, it's an oblique impact. And as we can see then, it rebounds in this direction here. So I've got this angle here, alpha, and we've also got this angle here, beta, okay? And just note as well here, we also have the impulse, right? So it goes towards the fixed surface here with speed u, and it leaves the fixed surface here with speed v, okay? So we can obviously explore this concept in quite a bit more detail here. So to finish with then, let's just quickly do that. So to continue here, you need to be aware then that when a smooth sphere collides with a smooth flat surface and bounces off it, the velocity of the sphere changes. And therefore then, as a result, the momentum also changes. Now the change in momentum is caused by the impact between the sphere and the surface. Now as the sphere and the surface are smooth, we know that the reaction between the sphere and the surface acts on the common normal at the point of contact. And as a result then, the impulse must also act in the same direction. And consequently, in the impact between a smooth sphere and a smooth fixed surface, the impulse on the sphere acts perpendicular to the surface through the center of the sphere. Now we can solve problems involving oblique impacts with fixed surfaces here by considering the components of the velocity of the sphere parallel and perpendicular to the surface. Now, the component of the velocity of the sphere parallel to the surface is unchanged. So in that case then, what we get here is v cos beta is equal to u cos alpha. And we can also use Newton's law of restitution here to find the component of the velocity of the sphere perpendicular to the surface. And in that case then, what we get here is v sine beta is equal to eu sine alpha, okay? What we can do here then is just eliminate u and v from the above relationship by dividing to obtain the following. So what I get here is v sine beta over v cos beta is equal to eu sine alpha all over u cos alpha. So clearly here what's going to happen then is the v's will cancel. I've got sine beta over cos beta, just basic trig identities here. We get tan beta. Again, on this side here, the u's will cancel. I've got sine alpha over cos alpha, so that gives me tan alpha here. So what we've got then is e times tan alpha. So in that case then, what we get here is tan beta is equal to e times tan alpha, okay? And since e, the coefficient of restitution here, must be between 0 and 1, in that case then, tan beta must be less than or equal to tan alpha, and therefore as a result then, beta must be less than or equal to alpha, okay? Now, I do appreciate here that there is quite a bit of information on this page, right? So please do make a note here of everything on this page. Now, there's a bit of a warning here. This final chapter on oblique impacts is a pretty challenging chapter and a pretty challenging topic. So what I'm going to say here is this chapter for most of you will probably be the most challenging part of Further Mechanics 1, and that is normal. So please do make notes here as we go through these videos, right? Do lots of practice, do, plenty of practice questions. It will get easier with time and the more practice you put in. But as I said, as a quick warning, it's not going to be easy for the most part, okay? So there we have it then. That gives everything that we need here for oblique impact with a fixed surface. So let's just put through a practice question together. So let's just get started then with the one practice question for this video. So what do we have then for this question here? Well, what we're told then is a small smooth ball of mass 4 kg is moving in the xy plane and it collides with a smooth fixed vertical wall which contains the y-axis. We're then told that the velocity of the ball just before impact is the following here. and the coefficient of restitution between the sphere and the wall is 1 over 4. Okay, so for this question, then we want to find the following three things here. As we can see, then we have three different parts, right? We've got part A here, part B here, and then finally part C, right? So let's just start then with part A here at the very top of the page, at the very top of the slide here. And first things first, as we can see here with this question, we don't have a diagram, right? So we don't have to draw a diagram here, but I would always recommend doing one. So let me just start here by drawing a quick diagram. It doesn't need to be perfect, by the way. But let's just quickly visualize this problem here. So we've got the ball, right, of mass 4 kg that's moving in the xy plane, and it collides with a smooth fixed vertical wall, which contains the y-axis. So basically, we have our wall like this, right, which contains the y-axis. It doesn't need to be perfect, but this here should just be a straight line. We then have our ball here. I'll just shade that like so. This travels towards the wall like so. It hits this wall here, our fixed surface, right, and it bounces off. Okay, something like this. Okay. Now what we know here is the initial velocity. That's this here, right, as a vector. So we have minus 4i minus 2j meters per second. These are vectors, by the way, the unit vectors here. So I'll just draw my squiggly lines underneath like so. And then for the velocity after the impact here, well, I don't know what that is, right? That's what we want to find here for part A. So for now then, what I'll do here is just let the velocity after impact be pi plus qj meters per second. Okay. So pi plus qj meters per second. Okay. And I'll just make a quick note here then. So as we've just said then, let the velocity after impact. Apologies, by the way, my handwriting is always shocking, but hopefully you can just read this. So let the velocity after impact be, as we've just said then, pi plus qj meters per second. Okay. So pi plus qj meters per second. Okay, perfect. So that's always a good starting point here, right? We're drawing the diagram for this problem here. And what we've also done here then is just let the velocity after impact be the following, right? So where do we go from here? Well, if we just think about this problem here then, and, you know, as we can see from our diagram here, the initial velocity is already in component form, right? So we've got one component parallel to the wall, and the other component is perpendicular to the wall. If you're struggling to see this here, just draw our unit vectors as we know them. We've got I here, like so, and we have j here, like so, right? So what that means then is parallel to the wall here. I'll just do this underneath them. So parallel to the wall here. So parallel to the wall then. Well, in that case here, if we're parallel to the wall, I can just simply see that Q must be equal to minus 2 as well, right? So parallel to the wall here, in that case then, Q will just simply be minus 2, like so. And then what about perpendicular to the wall here? So perpendicular to the wall, I'll just call this perp to the wall here. Just see me writing this out in full. So perp to the wall then. Well, if it's perpendicular to the wall here, in this case, P will be equal to, so we need to take into account here the coefficient of restitution between the sphere, or the ball here, and the wall. That's 1 over 4. So we take that as 1 over 4. And in this case here, the direction will change, right? Because we're bouncing from the wall. So we times this by 4 here, not minus 4. So just be very, very careful, right? So it's 1 over 4 times by 4. As I've just mentioned then, the direction of motion here is reversed, right? So 1 over 4 times by 4. No prizes for guessing here. P is 1. Okay. So to finish with them, we can just state here that the velocity of the ball after impact will be the following. So velocity velocity of ball after impact is, so what do we get here then? So I've got P here, which is just 1. So therefore, B here is equal to, I just get I here, right? So I, Q is minus 2, so I get I minus 2J meters per second. So I minus 2J meters per second. Okay. And there we go then. So this here gives us the solution to part A. Now, what about part B then? So for part B here, we want to find the kinetic energy lost as a result of the impact, right? Now, this is a very typical exam style question here. So we found the velocity of the ball immediately after the impact. We now want to find the kinetic energy lost as a result of the impact, right? So what I'll try and do here is just box this off ever so slightly, just so it doesn't hopefully cause too much confusion. So this here is for part A. Okay, I'll box it off like this. Okay, so let's just do part B underneath here. Hopefully this shouldn't cause too much confusion, but I'll amend it as I go if it does. So for part B then, what we need here is the speed of the ball before the impact and also the speed of the ball after the impact, right? Because for the kinetic energy of the ball before and after the impact, right, that would be a half mv squared. So let's just start then by finding the speed of the ball before the impact, and then we can find the kinetic energy of the ball before the impact as well. Let's make a note here. So speed of ball before impact. So the speed of the ball before impact here, nice and straightforward then, just simply an application of Pythagoras here, right? So we're using the initial velocity here, minus 4i minus 2j meters per second. So therefore, the speed here, I'll just denote this here underneath. That is equal to, it's the square root then of, as we just said here, minus 4 squared. Minus 4 squared plus minus 2 squared. So plus minus 2 squared, like so. We evaluate both of these, right? Add those together, and then we take the square root of the sum here. So what do we get here then? So that's 16, that's 4. 16 plus 4 is root 20. And root 20, we can simplify that, right? So that's root 5, root 4. Root 4 is 2. So I get 2 root 5 here. Okay. So the speed of the ball before the impact is 2 root 5 meters per second. Okay. And now that we've found the speed of the ball before the impact, we can now also find the kinetic energy of the ball before the impact. Okay. So again, I'll make another note here. The kinetic energy, which I'll just abbreviate to K dot E. Just save me writing this out in full then. So the kinetic energy of the ball before impact, will be, so you should be aware then that the kinetic energy of the ball before impact is just simply a half mv squared. That's a half mv squared, right? So what I get here then is a half times by the mass of the ball. In this case here, that's just simply 4, right? So I've got a half times by 4 times by v squared. So v here is just simply 2 root 5. So I've got half times by 4 times by 2 root 5 squared, like so. Let's just simplify this here then. So 2 root 5 times 2 root 5, or 2 times 2 is 4. Root 5 times root 5 is 5. So what's that? 4 times 5 is 20. Times that by 4, I get 80. Divide that by 2, and we get 40 there, right? So the kinetic energy of the ball before the impact is 40 joules. Okay, so 40 joules there. Perfect. We now just need to repeat this process again here, but now for the speed of the ball after the impact and also the kinetic energy of the ball after the impact. And from there, we can then find the kinetic energy lost. I appreciate these questions are quite methodical in a way, and there is quite a bit of work going into this question. As you can see, we're already at 10 minutes here for this question, and we're still halfway through part B, but we'll get there, right? We're nearly there now. So I'll do this part here in a different color. So now I want the speed of the ball after the impact. So speed of ball after the impact. So speed of ball after impact here. So clearly we're now going to use this velocity vector here, right? I minus 2j meters per second. Again, just simply an application of Pythagoras. So what we get here then is the square root then of, so I've got 1 squared here. So 1 squared plus minus 2 squared again. So plus minus 2 squared, like so. That is the worst square root sign ever, but I'll run with it for now. I'm not too bothered. 1 plus 4 is 5, so I get root 5 here. Clearly, I can't simplify that any further. I'll just leave it as it is. So I've got root 5 there for the speed, right? Don't forget our units as well. Root 5 meters per second. Perfect. And now, again, just repeating this process here. Let's just now find the kinetic energy of the ball after the impact. So just do that at the very bottom here. So kinetic energy, again, I'm going to abbreviate this here, of the ball after impact. After impact is, so what would that be? Again, it's just simply an application of a half mv squared. So I get a half times by the mass here, which is again 4. I've got half times by 4 times by root 5 squared. Times that by root 5 squared here. Root 5 squared is root 5 times root 5, which is just simply 5. Times that by 4, I get 20. Divide that by 2, and we get 10 joules here. Okay. And then finally, to finish with here, I'll just do this in a different color here then. Let's just do it in green then. So to finish with here, so therefore the loss of kinetic energy. So loss of kinetic energy. So loss of kinetic energy. That is equal to, it would just simply be 40 joules minus 10 joules, right? It's the difference here in the kinetic energy of the ball before impact and after impact. So I get 40 minus 10 here. Nice and straightforward, then that's just simply 30 joules here. Okay. And there we go then. So that gives us the solution to part B. And then finally to finish with here, again, just for one last time then, let's just kind of split the screen up here again. Kind of split it like this here. There should be plenty of room, I think, for part C. I'll just do part C over here. And again, I'll just do part C in a different color, just so you can differentiate a little bit more easily then between the different parts of this question. Let's just do it in blue here. Right, so for part C then, we now want to find the angle of deflection of the ball. So how do we find the angle of deflection of the ball here? Well, we can just simply use the scalar product here, right? So if I let theta be the angle of deflection, let's make a note here. So let theta be the angle of deflection. So we let theta be the angle of deflection. Then if we just use the scalar product here, then in that case, cos theta here is going to be equal to, so it's u, that's the initial velocity vector, dotted with v here. That would be this velocity vector here. And that's all over then the magnitude here of u, the initial velocity vector. So the magnitude of the initial velocity vector times by the magnitude of the final velocity vector. Okay. So nice and straightforward here then. What would we get? So in that case here, cos theta, I'll try this down in full then. So cos theta here is going to be equal to, so what I'd get here then is minus 4 times by 1, because the coefficient here of I is 1. So minus 4 times by 1. We're dotting these together, right? We've got minus 4 times by 1 plus them. So now dot the j components together. So I've got minus 2 times minus 2. So minus 2 times minus 2 here. And that's all over then the magnitude of the initial velocity vector times the magnitude of the final velocity vector. And we've already evaluated both of these, right? So this here is the magnitude of the initial velocity vector. So that's 2 root 5. So what I've got here then is 2 root 5 times by, where's the other one here? So that was this value, right? The speed of the ball after the impact. This here is the magnitude of the final velocity vector, right? Which is just simply root 5. So we get 2 root 5 times root 5 there. Okay. Now you might notice then straight away here, if we simplify the numerator then, that is minus 4 times 1. So that's minus 4 plus then minus 2 times minus 2. Well, minus 2 times minus 2 is positive 4. So what I've got here then is minus 4 plus 4, right? Minus 4 plus 4 is just simply 0. So all of this here is equal to 0. So cos theta is equal to 0. And in that case then, well, this simplifies quite nicely, right? If cos theta is equal to 0, and in that case theta is equal to cos inverse or arc cos, whichever you prefer, of 0. And in that case then, theta here is 90 degrees. Now, it won't always work out quite that nicely, right, where we get 90 degrees. Generally speaking, you are probably going to get a decimal. I've kind of written this question. It's kind of fluked quite nicely to give me 90 degrees. But like I said, generally speaking, you will probably get a decimal. That isn't to say that you can't get, say, 90 degrees, 60 degrees, 75 degrees, something like that, right? But generally speaking, as I already mentioned, you're probably going to get a decimal, okay? But there we have it then. So hopefully you can just about follow along with my work in here. So everything in the top right corner is for part A. Everything down here in the bottom left is for part B. And then finally, everything here, sort of like the bottom right corner, I guess, is for part C, right? And there we go then. So I can see here that we're at pretty much 17 and a half minutes here for this question alone. As you can see, these questions do take quite a bit of time. And this is certainly tricky, right? You know, this does take quite a bit of work to get to these solutions. But hopefully this demonstration here and the explanations for each part of this question did make sense. If there's anything that you're not too sure about, as always, please just leave a comment and I will try my best to help. But there we have it then. So that brings us to the end then of this video here on oblique impacts with a fixed surface. As always, thank you for watching.